I am the Stardust ESR number 15, Stefano Casini, and I'm currently working at Delft University of Technologies. And I'm going to guide you through my presentation following this outline. So I will introduce you the presentation, of course, then I will go into commercial off-the-shelf components for deep space CubeSat. And then I will focus on navigation requirements, autonomous optical navigation, and I will finally show you some simulation result and some conclusion of the talks. So before I start, for those of you who don't know what is a CubeSat, basically a CubeSat is a particular class of small satellites, and it is made up of one or more than one cubic unit of 10 by 10 by 10 centimeters, as you can see in the image in the slide. So we can have an assembly of only one cubic unit, so one U CubeSat, up to 27 U CubeSat. Usually CubeSat, they born for educational purposes, and they were used by the academia for educational purposes with students, I would say. But recently, they have been widely considered for many other purposes, such as scientific research. And in general, small satellite and so also CubeSat have seen an increasing interest, and many small satellites have been planned to be launched in the next years. But we have to remind that also CubeSat have been always considered around the Earth, especially the orbit, but recently they have also been considered for deep space application. The first two CubeSat that were launched a couple of years ago, and they were operating around Mars, were Marco A and B. So they basically demonstrated the feasibility of using CubeSat for deep space application, and they have been considered by the major space agency worldwide for asteroid exploration. As you can see in this picture, there are many designs under development. The reason why CubeSat are so interesting in the last years is basically the cost reason. So as you can see in this slide, the Marco CubeSat cost was around $18 million, which compared to a NASA mid-size mission, which is around $800 million, is really low. But of course, associated to a reduction in cost, we can see also a reduction in the lifetime of the spacecraft. And as you can imagine, also the scientific return that can be achieved with this kind of CubeSat. So now that you know what is a CubeSat, I would like to introduce you to my presentation, and I would like you to keep in mind two main questions that I will try to answer during the presentation. The first question is it possible to define a commercial off-the-shelf CubeSat architecture fully operational for asteroid exploration? While the second one is autonomous optical navigation via star trackers applicable to asteroid mission? So what I'm basically trying to do is try to show you that CubeSat mission is not a waste of time. So to start answering the first question, I defined a really challenging reference mission, which is an asteroid flyby. So basically an injection orbit around the Earth, followed by an Earth escape and a ballistic cruise towards an asteroid. And this kind of mission can be useful for the improving of near-Earth asteroid dataset via optical payload. I will try to stick my design within 3 U and 4 kilograms, and I want a fully autonomous and commercial off-the-shelf CubeSat. To preliminary design this kind of mission, I did use the JPL small body dataset search engine tool, which allow to define some important parameters for mission design. So as you can see in this table, you can have some candidates, some asteroid candidates as a target for the missions with their relative departure date and with the time of flight, which oscillate between 100 days up to also 900 days. But the main parameter that you should look at this table is the required escape velocity at the exit of the Earth sphere of influence, which can oscillate in these particular cases between 0.1 kilometers per second and 0.6 kilometers per second. These values then can be translated into engineering requirements, and so we can derive the required delta V to be performed performed at the delta V maneuver to be performed at the perigee of the SSGTO injection orbit to inject the spacecraft into an escape trajectory towards the asteroid. And you can see that if we stay below 0.4 kilometers per second, so 400 meters per second of delta V at the perigee, we will be able to reach up to around 0.8 kilometers per second as an exit velocity from the sphere of influence. So once we know that we can define this as a requirements for the delta V, we can talk a little bit about the chemical micro-revulsion system evaluation. To do that, I can show you here an evaluation chart in which the implicit coefficient for the plot is the delta V, while the explicit coefficient that you can see are the propellant mass of the engine and the specific impulse, while the blue lines represent the CubeSat beginning of life mass, increasing from left to right from 1 to 12 kilograms. And on the map, you can see plotted some stars and triangles, which represent respectively a monopropellant micropropulsion system and bipropellant micropropulsion system. To read this chart, it's easy and straightforward. For example, this engine, which is the MIPS, is with its standard configuration, is able to deliver 400 meters per second of delta V to a CubeSat with a beginning of life mass around 1 kilograms. So if you do remember, one of the requirements that I set at the beginning of the presentation, so that I want a CubeSat architecture with a mass less than 4 kilograms, you can see that this is the best candidate for the configuration, and it is the Aerojet Rocketdyne MPS 130. So other important subsystems that I want to show you in this presentation are the communication and power, which are always challenging for deep space application in general. And as you could see also in many other talks in these first 2 days. Talking about communication, I did consider some commercial off-the-shelf transmitters and antennas, and I built a really basic link budget based on the distance from the Earth. And as you can imagine, as long as the distance from the Earth increases, the available data rate decreases. So this is what you have to keep in mind, that we don't have a super large data rate, I would say. While the other subsystem that I want to show you in this slide is the power subsystem, so the available input power that can be achieved in function of the distance from the Earth. In particular, this plot has been obtained by using a configuration of deployable solar panels. And in the plot, you can see from top to bottom a decreasing incidence angle. And you can see, for example, that at 1 astronomical unit from the Sun, which is a fair distance for near-Earth asteroid operation, most likely we will be able to deliver to the spacecraft, to the CubeSat, slightly more than 30 watts. So without going in depth to other subsystem, you can see a table reporting all the commercial off-the-shelf components that can be used for this kind of application. And this configuration is within 3U and within 4 kilograms of mass. So I would say that to answer the first question that I gave you at the beginning of the presentation, I would say that yes, it is possible to design a commercial off-the-shelf CubeSat architecture for asteroid exploration, but we have some drawbacks that I would like to highlight you. In particular, they are related to the payload, which, as you can imagine, is the last commercial subsystem of each space mission. But in this particular case, there is only one infrared spectrometer which meet the mass and volume requirements, and there are few visible range cameras. But we can also highlight how Star Trekker's performances are really good for altitude determination, but their performances for autonomous navigation need to be assessed. Also, will the saturation and the spinning cannot rely on magnetotorquers in deep space, so this is another issue that should be addressed. And as I mentioned at the beginning, the micro-revulsion system still limit this application in terms of delta V. And is a small transmittable data set, but especially I want to stress the fact that commercial off-the-shelf components for CubeSat are designed for Earth application, especially LEO. So since this kind of spacecraft, this kind of CubeSat will undergo to a really different mission radiation profile, it is important to describe the radiation profile for a proper radiation hardening. So if I can move now to the second part of my presentation, which is the main focus of both my presentation and my personal project and my role also in the PWG Masse that you will see tomorrow. You will see tomorrow the presentation. Talking about autonomous navigation, I think we can define an autonomous navigation system as the set of hardware and software needed by the satellite to estimate its state on board without the need of ground tracking. So state on board, of course, I mean position and velocity. What are the pros and cons of autonomous navigation in general? Of course, it allows cheaper operation and mission, since indeed there is no need of ground tracking, so there is no need to pay people to work from ground, basically. And they will allow real-time navigation in deep space scenarios. But of course, the counterpart is that they need a really more robust design. There are many different kinds of autonomous navigation, but for deep space cruise, which is the main focus of this talk, the last three are the usable, and in particular I will focus on optical navigation, so how to use optical sensor to spot visible bodies in the field of view and retrieve information from them. So as you've seen from simulation to the presentation today, there are some phases of asteroid mission optical navigation. So I will go here really fast so we can consider an absolute navigation during the interplanetary cruise. The fast asteroid approach, so when the asteroid is basically just a few pixels in the field of view, so it is impossible to detect its feature. And the close proximity relative navigation, when the asteroid is well visible in the field of view and its features are detectable. And as I anticipated, I will focus on the absolute navigation during the interplanetary cruise. To do that, I'm using a particular kind of optical autonomous navigation, which is the line of sight navigation, which is based on capture images of the sky and look for visible objects, which can be planets, moons, or even asteroids. And from their direction, retrieve information for estimate the state of the observer, which is the spacecraft indeed. So to do that, I'm using an extended Raman filter. So basically, the filter is fed by the line of sight direction of visible bodies, which can be retrieved by star trackers images or camera images. In my particular cases, I want to stress the use of star trackers because they are always carried on board by satellites in general for altitude determination purposes. Together with the line of sight of the body, it is important to feed the navigation filter with the actual position from their ephemerides. So it is important to store on board the ephemerides of the body. And then it is possible to estimate the state, estimation that has to be iterated because of the light time delay and the light aberration. The main challenges that I do see in this particular navigation are, of course, related to the line of sight. So how to detect and identify within the field of view the object, how to spot as accurate as possible the centroid, and of course the tracking strategy. But also it is really important to optimally store on board the ephemerides of the bodies. So, talking about navigation during the interplanetary cruise, it's important to define the requirements. Of course, in general, it really depends on the particular mission, but in general, we can define for this particular application the requirements based on some hardware constraints, star tracker performances and propulsion capability, but also mission constraints due to the asteroid ephemerides uncertainties, payload constraints that I'm not considering, but in a real mission should be considered, and the all of these things should lead to the security requirements at the end of the cruise. So at the end of the cruise, I mean when we are switching between absolute navigation and relative navigation, I would say. So the first aspect that has to be taken into account are the uncertainties because of the asteroid ephemeris. Because as you can imagine, if we want a fully autonomous navigation system, a fully autonomous CubeSat, it will not be able to receive updated information on the target asteroid ephemeris. So it will have to rely on the propagated ephemeris stored on board previous to the launch time. So to have a rough idea of these uncertainties, I perform a 300 days propagation in the full body problem, taking the initial condition from the well-known NeoDis 2 portal, and this initial condition were referring to the 31st of May 2020. So I took as an example two asteroids, Eros indeed, in which you can see a rough error below 200 kilometers. And if we do propagate the ephemeris, we see that also the uncertainties grows at the flyby time, and we are slightly below 2000 kilometers, so 1 order of magnitude increasing. The same behavior is possible to see for the asteroid 2059, in which we have an initial uncertainties below 100 kilometers, which translated into a propagated uncertainties around 1,500 kilometers. So also in this case, you can see an increase by an order of magnitude of the ephemeris uncertainties, at least in one component. Of course, this is not a two-body problem propagation. It's not the most accurate kind of propagation, but it is important just to have a rough idea of the uncertainties increasing. The second aspect that I want you to keep in mind is the asteroid detectability, because if we want to use star trackers to track asteroid also during the far approach, we have to keep in mind that microstar trackers have a limit on the visible magnitude, usually well below 7. And asteroids are really faint objects. So we should ask ourselves how many days before the flyby the asteroid appears in the field of view. To do that, I using the same asteroid of the uncertainty ellipsoid, I performed a study in function of the phase angle and the distance asteroid sun, which influence, of course, the brightness of the body. And with a linear approximation, I define how many days before the flyby the asteroid appears in the field of view. So for Eros, you can see that it can be, in the very optimistic case, 9 days before the flyby, up to 3 days before the flyby. While for the asteroid 2059, it's not even 1 day in the best case scenario. So we have to keep in mind also this. And finally, the delta V capabilities. So basically, when we are entering the last phase of the flyby mission, so we should have to correct the trajectory of the spacecraft, which has to be corrected because of the uncertainties in the position of the spacecraft and in the position of the target asteroid. The delta V capabilities indeed influence the achievable displacement performing the maneuver. In this case, I'm considering 8 days before the flyby. So if the asteroid will be visible in the field of view 8 days before the flyby, which, as I told you, is very optimistic. And I performed a study in function of the in-plane, out-of-plane angles and intensity of the maneuver. And as you can see, as long as the intensity of the maneuver increases, so we can arrive up to 10 to the 4 kilometers of displacement at the flyby time by performing a maneuver 8 days before the flyby. But if we have a lower available delta V budget, we will achieve really tiny displacement. So based on what I told you in the previous slide, it is important to define the navigation requirements. I see Giulio showing up, so I guess I have 10 minutes. So each asteroid has different characteristics, which translate into different hardware constraints and different accuracy requirements. But in general, just to have a rough number to deal with navigation filter, it is reasonable to assume assume navigation requirements around 1,000 kilometers in position and 10 to the minus 4 kilometers per second in velocity with a 3 sigma accuracy. So it is legit to ask ourselves if autonomous line of sight navigation via star trackers is able to ensure this accuracy. To do that, I perform some simulation. This is the setup. I basically generate some high fidelity trajectory with 2 data with this initial condition. And here you can see the trajectory of the spacecraft in light blue, while the other trajectories are the orbit of the planets. And I did generate high fidelity trajectory because, and not using the two-body problem in order to obtain a more realistic simulation. So to generate observables for the simulation, I do use an high fidelity trajectory. And here you can see the net effect between propagating the CubeSat position and velocity with high fidelity and two-body. Here the position and here the 3 velocity components. And these are the main characteristics of the simulation. So I'm using a high trust application, 300 days propagation, an observation rate of 1 per hour with a measurements accuracy of 3 sigma accuracy of 10 rsec, and the initial position uncertainty of 10 to the 5 in kilometers and 10 to the minus 1 in velocity, kilometers per second in velocity. So another reasonable question, as I was mentioning you at the beginning, is the tracking strategy. So the first tracking strategy asset has to be which body to track. This is what happened when we track Venus. So we see a strong increase in the accuracy evaluation of the position and velocity of the spacecraft. If we zoom in the last 60 days, we can see that we can reach an accuracy in the X position, for example, of 10 to the 4 kilometers in the X component, while we are around 10 to the minus 3 kilometers per second in velocity. So we are going fast to this. It means that maybe one body is not enough to be tracked for line of sight navigation. And indeed, these are the results if we do track Jupiter and Mars at the same time. And if we zoom again in the last 60 days, we can see an accuracy in the order of the requirements, navigation requirements that I defined before. So in the order of 1,000, 2,000 kilometers for the position components, and 10 to the minus 4 or less than 10 to the minus 3 in the velocity components. So to conclude, I would say that line of sight less than navigation is a mature technique for autonomous asteroid exploration, but the use of star tracker, of course, has to be assessed to prove the accuracy assumption in the simulation. And as I mentioned you before, optimal tracking strategy has to be assessed. And also, I did consider a ballistic transfer, while low thrust trajectory may require a passive tracking strategy. To conclude, deep space CubeSat, autonomous deep space CubeSat are a challenging and cheap solution to explore asteroids. And I'm sure that will open solar system exploration to the scientific community. So thank you for the attention. And if you have any question, I will be happy to answer.
Thank you, Stefano. You are perfectly on time. So we have 5 minutes for questions.